Welcome everyone to day 5 of the Spring 2021 Celebration of Mind Talks. I'm your host, Bob Hearn. It's my great pleasure to introduce Robert Fathauer. Robert is a longtime attendee of both Gathering for Gardner and the Bridges Math Art Conference. He has a lifelong interest in tessellations, is one of the world experts. He's founded a business, Tessellations, you can find at tessellations.com, and has an incredible new book on tessellations that I think we're going to see a little bit from. So without further ado, Robert, feel free to begin.
Thanks for the introduction, Bob. Tessellations is a broad topic. I'll give an overview today and go into a little more detail on a couple of aspects of that. Again, my name is Robert Fathauer. My small business is called Tessellations. I really got interested in this topic more than 30 years ago. I started the business almost that long ago. I have an online store called mathartfun.com and also a polyhedral dice brand called the Dice Lab. And that's a collaboration with Henry Segerman. So I recently finished a book on this topic. It was just came out from CRC Press. This is a flip through. It's about 450 pages long. It's full color. It comprehensively covers the topic and focuses down on some special interests of mine that I've worked on a lot over the years: fractal tessellations, Escher-like tessellations, applying Escher tessellations to polyhedra. One feature of the book is activities in the back of each chapter, which are suitable for classroom use. And this is widely available at Amazon, for example. If you want a signed copy, you can buy it through my online store. So let's start with some basic concepts and definitions so we're all on the same page. A tessellation or tiling is a collection of shapes called tiles that fit together without gaps or overlaps to cover the infinite mathematical plane. So a drawing like this should be understood to extend to infinity in all directions. This shape is called a tile. There's an interior. It's got a boundary. If it's a polygonal tile, it has corners. It has edges. Where 3 or more tiles meet, that's called a vertex. And the number of tiles meeting on a vertex is called the valence or order of the vertex. If all the tiles meet along their full edges, that's called an edge-to-edge tiling. So one way to systematically explore a given set of tiles is by looking at the possible vertices you can form. These are all the possible vertices using regular polygons. They're divided into 4 groups here. These 3 are the regular tessellations, which means all the polygons are of the same type and all fit together the same way. These are the semi-regular or Archimedean tessellations. There are 8 of those. This is simply a specification for in terms of the polygons meeting on a vertex. So like this just means 3, 6, 3, 6 is number of sides. This 3rd group shows vertex groups that appear in tessellations, but not semi-regular or regular ones. And the 4th group are vertex groups that do not appear in any known tessellation of regular polygons. So these are the 3 regular and 8 semi-regular tessellations. The dual of a tessellation is the tessellation obtained by connecting the midpoints of adjacent tiles. That looks like that. And if I drop the background out, these are collectively known as the Lave's tessellations. A lot of these concepts are also found in polyhedra in 3 dimensions. So you could have a dual of a polyhedron and all this kind of stuff, if you're familiar with polyhedra. Symmetry obviously plays an important role. Tessellations that repeat in the plane, which are known as periodic, can have 3 basic types of symmetry. The first is translation. That means if you translate the entire tessellation in some direction by some amount, it will perfectly overlay itself. So any of these arrows will serve that purpose. Such an arrow is known as a vector. The second type is rotational symmetry. This is a point of 6-fold rotational symmetry. You can rotate the entire tessellation about this point by 1/6 of a full revolution, and it will overlay itself. And these are points of 3-fold rotational symmetry. And finally, we have glide reflection symmetry. If you glide or translate by this amount along this line and then reflect, the tessellation will overlay itself. A special case of this is simple reflection or mirror symmetry, where the glide distance is 0, and this is a line of mirror symmetry. It's been shown that periodic tessellations or patterns in general must belong to one of the 17 so-called wallpaper symmetry groups. A symmetry group is a collection of symmetry operations. So a particular group might have 3, 2, and 6-fold rotational symmetry. Coloring is another important aspect of tessellations. For clarity, tessellations are frequently colored such that adjacent tiles are not the same color. A two-colorable tessellation is one for which 2 colors suffices to meet this condition. There are 2 examples here. Note, in each of these, every vertex has valence 4. You could have a mixture of even valences, 4, 8, 12. But as long as every vertex has even valence, you can 2-color it. Here are 2 tessellations that require 3 colors, and finally 2 that require 4 colors. It's been shown, proven that at most 4 colors are required for any tessellation. You could also put symmetry constraints on your colors so that, for example, if you translate and flip about this line, the colors have to overlap, and that would change your color requirements. You might need more than 4 colors in that case. Well, tessellations have many both practical and decorative applications, and they're found in all cultures from very early on. The most obvious application of tiling, of course, is tiling. We probably, at least most of us, if not all, have tiles in our house, floors, countertops, a shower stall, whatever. Those are usually something pretty dull, like a regular tessellation of squares or maybe octagons and squares. But you can also have quite complex and beautiful tessellations or tilings in the real world. This is a public fountain in Morocco. These are tilings of bricks. These are all in the Netherlands, and none of these are edge to edge. So note that this edge of the brick matches half the edge of this one. So it's not edge to edge because all edges do not fully match up. This is a street paving in a square in Funchal, Madeira. This is obviously a 2-colorable tessellation. And it's fun to try to find these as you travel around. These are all photographs I've taken myself in my travels. This is a utility cover for the Japanese telephone company in Tokyo. And it's a tessellation of the letter T. This is a glass covering of the courtyard of the British Museum. And real-world tessellations are not mathematically perfect. You know, the lines in between tiles have finite thickness. The shapes aren't perfect triangles or whatever. And those imperfections are even more pronounced, of course, in tessellations in the natural world for the most part. This is known as the tessellated pavement. It's on the coast of Tasmania. And this is just a natural rock pattern that results from geological processes. Another example in nature is the scales found in lizards, snakes, and the like. The divisions in the dragonfly's wing are one of my personal favorites. A lot of really interesting stuff going on there if you look at the number of sides and how they meet. The spots on a giraffe are another example. Okay, so we've talked a lot about regular polygons. Regular polygon is one where all the sides are the same length and all the angles are the same. For making, I think, aesthetically attractive tessellations, star polygons are particularly nice as well. Some of the more symmetric star polygons can be obtained by starting with a regular polygon, either through stellation or by drawing diagonals. In stellation, you extend edges, and those form stars. So here's one 8-pointed star with 90-degree tips. And there's another 8-pointed star that has actually 45-degree tips. You can also get those by drawing diagonals inside a regular polygon. So this is an octagon, a regular 8gon, and this is known as the first stellation and the second stellation. And this concept, again, is also found in polyhedra. There are a wide variety of beautiful tessellations that combine star polygons with regular polygons. And here's a dozen examples. This one I especially like because it is regular nonagons, which you just don't see very often. Islamic art is especially noteworthy for its use of sophisticated tessellations involving star polygons. They usually have other types of less regular polygons mixed in. Often they will divide star polygons like this. So you have kites and then a smaller star inside of it. And the other characteristic shapes you see, which have names. This shape is common, this kind of partial star. Sometimes you'll get distorted stars to make things work in a way that doesn't really, work with regular stars. And often you'll see interwoven lattice designs based on these. And these kind of things can be found in mosques and other buildings that are many centuries old throughout the Middle East. Some tessellations involving star polygons work for a variety of different star angles. This is a tessellation in which every corner of a tile is also a vertex of the tessellation. And this will actually work for any shape of three-pointed star. There's a few examples with thicker stars. And you could actually continue till these are convex polygons as well. So let me move on to some other concepts. These are three related concepts that are a little bit harder to describe maybe. The first is the idea of a self-replicating tile, or rep tile for short. And that's simply a tile that can be divided into smaller copies of itself. So one simple example is the El Tromino, which is a shape made up of 3 squares. It's called a tromino in analogy to a domino made up of 2 squares. You can divide a tromino into 4 smaller trominos as shown here. Here I blew the whole thing up to make it visible. But if you repeat that, divide each of these 4 into 4, you get 16 of these shapes. You repeat again, you get 64, 256. You can carry this out as long as you want and get an arbitrarily large, what's called a patch of tiles. And that's equivalent to saying you can tile the entire mathematical plane. So in a limit of iterating an infinite number of times, you have tiled the entire plane. But note that this is not a periodic or repeating tessellation. It may seem a little counterintuitive to think that an infinite tiling never repeats, but that is possible. This particular tile could tile in a repeating fashion. So if all the tiles were oriented this way, for example, it would be a repeating tessellation. Of more interest are sets of tiles that only tile in non-periodic fashion. Those are called aperiodic sets. So this process here is called substitution. Substitution is a nice way to obtain non-periodic tilings. And it's actually been a topic of some interest to tiling mathematicians in recent years. And there are mathematicians that specialize in tiling. It's a relatively small community. So tiling is a nice topic, and then it has these practical applications like tiling your floor. It's got this serious mathematics, and also has this kind of recreational stuff, a lot of fun math. And it's also good for games like game boards, etc. So people have found aperiodic sets of tiles, most of which had a very large number of tiles. But Roger Penrose in 1974 discovered a set, actually 2 related sets of 2 tiles that only tile non-periodically. This is the more popular of those 2. It's called kites and darts. So this is a kite and that's a dart. These show different possibilities for mating 2 of these tiles in edge-to-edge fashion. Well, Penrose imposed matching rules which forced these to tile non-periodically. So none of these matchings are allowed, and all of these are. And to enforce matching rules, you could either modify the tiles, like by putting little notches in it, for example, or you could mark or decorate the tiles to enforce the matching rules. I think that's a little more elegant. This shows a decoration with knot type graphics. And so the rule is that these strands have to be continuous across boundaries. And you can see that you form this kind of nice knotwork kind of patterns. This is what mathematicians would call a link, because a knot only has 1 strand. And this is an alternating link, or alternating links. So if you trace one of these, it always goes under, over, under, over, under, over. Penrose tiles have a lot of interesting, fun properties. These show the angles in the 2 tiles. The ratio of long to short edges is in the golden ratio, or golden mean, 1 plus the square root of 5 over 2. In addition, in any infinite tiling of Penrose tiles, the ratio of kites to darts is exactly the golden ratio, which is an irrational number. So that's kind of an interesting thing to try to wrap your head around. Another important feature of Penrose tiles is inflation and deflation, which is another word for substitution, really. You can also call this composition and decomposition. So the rules for these tiles are as follows. The kite, who's a large kite, it breaks into 2 smaller kites and 2 half darts in this manner. And a dart breaks into 1 kite and 2 half darts. And that gives you a new tiling with smaller tiles, a larger number of smaller tiles. This pattern with 5 kites at the center is called the infinite sun pattern. The pattern with 5 stars is called the infinite star. And as you inflate repeatedly, you switch back and forth between these two. Many of the recreational aspects of Penrose tiles were worked out by John Conway, and Martin Gardner wrote about these in the January 1977 issue of Scientific American. And in fact, the cover of that issue is a Penrose tiling. Here's a larger patch of the Penrose tiling. This is known as the Cartwheel tiling. There's a lot of terminology with these things. So this bit in the center, this regular enclosed by regular pentagon, is called a decapod. In the center of the decapod, we have what's known as the Batman figure. The cartwheel has spokes, and the spokes consist of long bow ties and short bow ties. So those are a lot of fun to explore, and just an example of kind of recreational mathematics using tiling. So moving on to Escher-like tiles based on real-world motifs, which I call Escheresque, are created by reshaping the boundaries of geometric tilings and adding interior details. And M.C. Escher is famous for his tessellations of birds, lizards, other creatures, people sometimes. And these are fun to play around with. The book has a lot of templates and instructions for making these with different types of symmetry. I'll walk you through one example here. This is a template that creates a tessellation with a glide reflection symmetry based on a square lattice. So this is your kind of starting template, just a square. We have 2 independent line segments, A and B. A is simply the same from one side to the other. B is the same from one side to the other, and A, when it translates over, flips top to bottom. So there's a reflection on the A side. So here you see this distortion of B is the same top and bottom, and the distortion of A is flipped top to bottom. So when you design this using the templates in the book, you create a physical template like this. And I'll show some photos of how this works. So I start with a grid. I do some sort of just random lines. And this is typical if I design tessellations, though I don't do them on paper, do them on computer, but I start with some shape and maybe distort it. And then I'll say, oh, it looks a little bit like a fish maybe. And so I'll sketch some interior details and say, well, it would look more fish-like if I did this or that. So I'll change the boundary to be a little more fish-like, and then I'll refine the interior details. And it's back and forth process that goes through many iterations till you get something you're happy with. In this particular tessellation, half the tiles are upside down. If I made them all the same, I'd have half my fish swimming right side up and half my fish swimming upside down. And that, to me, isn't very pleasing. So what I did was with the upside down motif, I broke it into two fish that are both right side up. And so you make your paper or cardstock template with that, and you use that with a grid to draw the larger tessellation just by tracing with a pencil if you're doing this by hand. And then I sketch in the interior details lightly with a pencil, then I ink them in with a pen. And then here I shaded that with colored pencils. Down here I scanned in this and dropped in buckets of color using Photoshop. And lots of different ways to make these and to render them. Here are some examples of tessellations I've designed over the years. This is a fish design. It has 3 points of threefold rotational symmetry, one where 3 jaws come together, one where 3 fins come together, one where 3 tails come together. And if you connect these 3, you get an equilateral triangle. This is a lion tessellation that has glide reflection symmetry. Here's a tessellation of frogs. This has 4 distinct points of twofold rotational symmetry. One where 2 right arms come together. Here we have 2 right legs coming together. Here 2 left legs, and here 2 left hands or arms. And this example is a tessellation morph. There's a tessellation of dragons in the center that has glide reflection symmetry, but I morph continuously from more realistic dragons to more realistic black dragons to more realistic white dragons. And this involves something Escher used quite a bit, which is a ground figure reversal. So here you have black figures on a white ground, and here you have white figures on a black ground. And as your eye scans around, your brain has to flip interpretation as to which is figure and which is ground. So it's kind of a form of optical illusion. Here's one with a vanishing point at the center, a flower and leaf tessellation. That's based on a kite tiling rosette. This is the angel and devil design. This is based on a more complicated template, which is a fractal arrangement of circles. So I won't try to describe that right now. So another thing you can do with planar tessellations is apply them to polyhedra, to decorate polyhedra. So a polyhedron is a solid, the faces of which are polygons. And the polyhedron we're most familiar with is simply a cube. It has 6 faces, each is a square, a regular four-gon. So a diagram that you can cut out and fold up to make a polyhedron is called a net. This is a net of a cube cut in 2 pieces for practical reasons. So the question is, how do you fit a tessellation to this so that it still matches up seamlessly when you fold up your net? These are squares, so you probably want to use a square template. A square 2-dimensional tessellation, recall, has 4 squares meeting at each vertex. And in a cube, you have 3 squares meeting at each vertex. So you're going to need a tessellation that will allow this to still work when you fold it up. Here's a tessellation of seahorses and eels. And these are points of 4-fold rotational symmetry. There's 2 distinct types, one where 4 seahorse tails come together, one where 4 eel tails come together. And since you have 4 motifs meeting here, if you cut out one of the 4, you'll have 3 meeting there, and it should still be seamless. So I'm going to arrange this so that this is a face of the cube. So applying that in color version to my net, you get this. Notice these 4-fold rotation points are at the corners of the cube, and that looks like this. So you do have now points of 3-fold instead of 4-fold rotational symmetry. And of the 8 corners of the cube, 4 are points where 3 eels meet and 4 points where 3 seahorses meet. And this is a computer graphic, but you can actually physically make these using the templates in my book. This is a photograph of a actual paper model. This is called a Rhombic Twiliocontahedron, which means it has 30 faces. Each of them is a rhombus. Note that on each rhombic face, there are 2 complete lizards broken in halves. So there are 60 lizards distributed over this shape. Physically, this is about that big. And you can actually make this if you'd like. Go to celebrationofmind.org/archives/913. And there's a template you can use to make this particular polyhedron. So I'll talk a little bit about another more advanced concepts. I've talked so far about planar tessellations, tessellations in the Euclidean plane. We're all used to Euclidean 2- and 3-dimensional space. That's how we kind of see things. Though you can actually talk about also different types of non-Euclidean geometry, such as spherical geometry and hyperbolic geometry. And in fact, we live on a sphere. It just looks like a plane to us because we're small compared to the size of the Earth. So here's a polyhedron known as an icosahedron that has 20 faces, each of which is an equilateral triangle. And there are points of 5-fold symmetry, 2-fold symmetry, and 3-fold symmetry. If you fit a tessellation with that same symmetry on there, you can get a tessellated icosahedron. This is a starfish and shell motifs. And to make a spherical tessellation, just think of kind of expanding this like a balloon, or mathematically you say projecting it onto the surface of a sphere. And you have the same symmetries in the spherical tessellation here. So spherical tessellations kind of go one direction from planar tessellations, In the other directions, you could say we have hyperbolic tessellations. This is a harder concept to grasp, but I want to try to explain it. I'll just say that this is a model of the hyperbolic plane. This is called a Poincare disk. And this shows the entire infinite plane in a finite circle, which is nice, a nice way to see an infinite tessellation. One thing I'll point out as far as properties that distinguish these, as we learned in school, in Euclidean geometry, the angles in a triangle sum to 180 degrees. Well, in spherical geometry, the angles in a triangle sum to more than 180 degrees. And in hyperbolic geometry, they sum to less than 180 degrees. So let's look at regular tessellations in that broader context. You can specify a regular tessellation with two numbers using the Schläfli symbol, nk. So the first number, which n is 6 in this case, that's simply the number of sides of the regular polygon. And the second number, 3, is simply the number of polygons that meet in a vertex. So this is 6, 3. The regular square tessellation is 4, 4. And the triangle tessellation is 3 sides, and 6 at the vertex. If we make a plot, we can plot number of polygon sides n on this axis. 3 is the minimum number of sides for polygons. So we have 3, 4, 5, 6, and it keeps going, 7, 8, 9. Down here, we plot number of polygons meeting at the vertex. Again, 3 is the minimum possible. We have 3, 4, 5, 6, and it keeps going. So there's only 3 Euclidean regular tessellations, but there are 5 spherical regular tessellations, and I'm showing these both in spherical and polyhedral form. In polyhedral form, these are known as the Platonic Solids, which is a term you may have heard. The cube is one of those, the dodecahedron another one, etc. And the other ones, the other 8 here, and in fact, continuing to bigger n and k, there are an infinite number of hyperbolic regular tessellations. And these make for pretty images, I guess. These are 3 different spherical tessellations using the same flower and leaf motif. These are some geometric hyperbolic tessellations using different models of the hyperbolic plane. This is called the half-plane model. This is the conformal square model. This is the band model of the hyperbolic plane. Now, I'll just briefly touch on fractal tessellations, a particular obsession or hobby of mine. I spent many hours playing around and discovering these. These look kind of like hyperbolic tessellations, but they're not. They live in the Euclidean plane, but they're bounded, and typically the boundary is fractal. All the tiles are similar, which means the same shape, but not necessarily the same size. And here's just a few examples. These examples are edge to edge. There's an Escher-like one with birds and snakes. And this figure is formed by repeatedly removing and building back in with tiles, which I won't try to describe in detail. Just want to convey some of the beauty in those types of figures. I'm going to conclude there. This is my email address, rob@tessellations.com. My art site is robertfathauer.com. I also do ceramic sculpture. You can see a few behind me. Try to point those out. These are my Facebook and Twitter handles. I have a bunch of recreational stuff on fractaldiversions.com, including fractal tilings, fractal gaskets based on reptiles, dendritic tiles, and other stuff. And finally, the website about the book is shown here. So I will thank you for listening and open it up to questions.
First question we have, I believe you've already answered. Are there any interesting results for tiling other manifolds besides planes? You went into that in some detail, although I'm not sure, they might have been asking about higher dimensional manifolds, perhaps?
The concept of tessellations is not limited to 2 dimensions. In 3 dimensions, for example, there are polyhedra, which tile 3-dimensional space. The most obvious and simple example is the cube. You can stack cubes in a way that there are no gaps and no overlaps and tile 3-dimensional space with cubes. You can also do that with some other polyhedra, a rhombic dodecahedron, for example. And these concepts can be extended to even higher dimensions than 3. That gets difficult to describe and visualize, of course.
The next question, you move to tiles with curved edges. Is there theory to characterize how the curved edges interact?
You can obviously have curved edges. It's easier to talk about straight edges, and people have studied straight edge tilings. For example, a few years ago, Casey Mann and his students discovered a new distinct tiling of the plane by pentagons. It was the 15th and has now been proven to be the last distinct tiling by pentagons. So mathematicians like to characterize things, and it's easier to deal with polygons, I think. Replacing edges with curves is more like Escherizing tiles. So I'm not sure how to characterize what interaction means or what the question is getting at there, but you could certainly have curved edges.
So about the tiling on other manifolds, Paul clarified he was asking about higher genus surfaces.
Yes, I've not done much of this myself, but people have done things like tile a torus or tile something called higher genus. If you don't know what that means, like imagine a torus, kind of a torus with multiple holes in it. That's a higher genus surface. Carlos Sagan has done some work with tiling more complex surfaces. You can easily find him. He's a professor at Berkeley. You can easily Google and find some of his papers on that. Or go to the Bridges website, bridgesmathart.org, click on the archive, and you can search all of the papers presented at Bridges in its 23-year history or something. So you can enter search terms or enter a name and pull up papers on that type of topic that way.
Is there any interesting work on animated tessellations?
Yes, especially in recent years. Animated tilings does a lot. If you're on Twitter, I've actually posted several myself. Craig Kaplan has done some, and I wrote a Bridges paper about him recently. I guess it's not published yet. Other people have done very nice animated tessellations. If you get on like Twitter, like Bees and Bombs is one handle. There are other names. Craig Kaplan actually had a kind of a contest to do tessellation animations and transformations using squares, and many people responded to that. There's been some work on animated Escher-like tessellations. Nakamura in Japan has done some. Again, I think if you just search, you can find some stuff. There's actually a Japanese tessellation society. Yoshi Araki is involved in that, has probably done some animations. He's also on Twitter and Facebook. Facebook has a mathematical tiling and tessellations group. There's a Bridges group on Facebook. You can find these kinds of things on those places.
Next question, is there a fractal unbounded tessellation of the Euclidean plane?
Yeah, you can. There's a couple kinds of fractal tessellations. What I showed was a fractal arrangement of polygonal tiles. You could also have fractal tiles, which can tile conventionally or tile in fractal fashion. You could do some sort of substitution and have a very complex fractal tiling of the entire plane that was not bounded. They could have, I don't know, infinite number of singularities. So there are things you can do. It's not as necessarily bounded. And there are also some of those bounded fractal tessellations I've done will fit together as tiles. So you could tile the plane with those fractal tessellations, which would cover the entire plane, and the boundary between them would be a fractal line of singularities, singular points. A singular point or singularity is a point at which the tiles become infinitesimally small, basically. So if you plotted like number of tiles along a line that passed through singularity, it would go to infinity at a point, like a delta function, if you're more familiar with physics and math kind of things.
Ed Pegg notes that he will discuss fractal tilings in his talk later today, if you're interested. I want to interject a question of my own. You talked about Penrose tiles, aperiodic tile sets with only 2 tiles. of course, this is one of the most famous open problems in tiling is there a single tile that only tiles aperiodically? And we had a talk about that several years ago at Gardner. There's as I recall, there's a discontinuous tile.
There is a tile, yeah, discontinuous aperiodic monotile. There's no well-behaved monotile at this point in time. It's an open problem, yeah.
The so-called Einstein problem, I believe.
Yes, Joshua Soklar in conjunction with
yes, right,
woman in Australia whose name I've forgotten, unfortunately. I think we're behind that one. I should mention that Penrose, Roger Penrose is famous. He's just won the Nobel Prize. He's a Knight of the Realm, et cetera, et cetera. Theoretical physicist. But about the same time, a postal worker, an amateur mathematician named Robert Aumann was exploring aperiodic sets. He independently came up with some 2-tile sets, and he wrote to Martin Gardner after seeing Gardner's column on Penrose's tiles. And I think Martin subsequently talked about Robert Aumann's work in his column. So I think it's quite remarkable this amateur working at the post office did this stuff at the same time independently as this famous university.
Could a spiral tessellation have any meaning?
I've actually done a lot with spiral tessellations myself in the last 2 years or so, especially tessellation of triangles, different types of spiral tessellations of triangles, and also quadrilaterals. Those have a singular point at the center where the tiles get infinitesimally small, and they keep going to cover the entire mathematical plane. So they're not a well-behaved tessellation because they contain a singular point, but it doesn't bother me. And they're quite nice actually for Escher-like diagrams. You can have double-ended spirals, which are very attractive for art. You can create those with Mobius transformations too, if you know what those are. So spiral tessellations are quite, I think, nice aesthetically. And spirals are very attractive aesthetically. I think tiling mathematicians are not as interested in that kind of thing.
So we have a question. Could you suggest some first programming steps for students who want to explore tessellations?
Programming, there's a lot of stuff online now. You can also certainly use general mathematical software like GeoGebra or Mathematica. Kevin Lee wrote a program called Tesselmaniac, which is specifically designed for creating Escher-like tessellations. It's got a bunch of templates, and you can just distort the tile and drop in eyeballs and stuff, make it quite easy. And he even actually allows you to output files to laser cut tiles using your designs.
Do you know of any software that allows construction of zonahedra?
Zonahedra? There's a Zome tool based program called VZome written by Scott Vorthman.
Yes.
So that might be the best one. You can do zonahedra in Mathematica too, or probably any general 3-dimensional mathy software, whatever your favorite is.
Any other book recommendations on math and art to inspire kids about math and not just tessellation?
I should certainly give a nod. I was sitting here to a book called Tilings and Patterns, written by Grinbaum and Shepard. That has been the Bible of the tiling of the topic for many years. It was written in the 70s, I think. It's not an easy read. It's written on a rigorous mathematical level with proofs and stuff, but it has lots of figures, comprehensive figures. Unfortunately, all black and white. I have a lot of the same figures in my book in color. So Tilings and Patterns is a classic text on that topic. But the question was on what kind of book now exactly?
On math and art to inspire kids about math and not just tessellation.
There's some good coloring books. Edmund Harris, I don't know if Edmund is listening, but Edmund Harris has written one in collaboration with Alec Bellows, Another one he wrote, I have some figures in some of those. I've actually got some of my own activity books. One just has my own Escher-like tessellations in black and white. You can color those. Another one has regular polygon tessellations in black and white. And you can just use it as a coloring book, but you could also like drawing lines of symmetry and points of rotational symmetry and learned about tessellations that way. Jenny Beyer has done some tessellation stuff that's geared at quilters. Quilting is another very long standing application of tessellations. A lot of the fiber arts, decorative arts, basketry, just cloth, physical wallpaper in your house. There's just so many places you see tessellations in the real world.
Yes. So we still have a lot of questions coming in, so I'm going to move forward. This next one I think gets back at the wallpaper groups. What symmetrical numbers of folds can work together and which cannot? For example, 3-fold and 6-fold can work together, can 3 and 4, 2 and 5, etc.
There are no repeating patterns with 5-fold rotational symmetry. That's been proven. Interestingly, the scientific world was kind of shocked. I was in graduate school in the mid-'80s when 5-fold diffraction patterns were discovered because they're just not mathematically possible. And it turns out people ended up using Penrose tiles to model those. So you have some kind of quasi-periodicity that can give you 5-fold.
That's actually related to my my background. It's a pattern that has 5-fold rotational symmetry about 2 different points within a restricted radius.
But there are no repeating patterns that have 5-fold or anything other than 2, 3, and 6-fold rotational symmetry.
Yeah.
And that's been proven mathematically.
Yeah, crystallographic restriction theorem. What suggestions do you have for students interested in 3D printing flat tessellating tiles? I would think laser cutting would be a better idea, but.
Yeah, for 2-dimensional stuff, laser cutting is simpler. You could certainly 3D print tiles though. You just need a 2-dimensional shape that's thickened. You can make that easily in things like Mathematica, whatever your favorite kind of 3D software is. I imagine there's stuff on Thingiverse, for example, and that you can find.
We have a request to see some of your ceramic pieces close up, if you could talk about them a little bit.
Oh, okay. I do hand-built ceramics. I've been doing that for about 8 years now. This is a Mobius band with 3 half twists. So if you give a band a band has 2 sides. If you give it a half twist and join it, it has 1 side. That's called a Mobius strip. If you give it 2 half twists, it has 2 sides again. If you give it 3 half twists, it has 1 side. So this is a 1-sided object. This is something called a hyperbolic hyperboloid. So hyperboloid is kind of like a helix. And this is a helix in hyperbolic projection. So like in a sphere, that's kind of the 3-dimensional analog of the Poincare disk. This one is a polyhedron. This is a polyhedron with 24 faces. Each is a pentagon. It's called a pentagonal icosatetrahedron. And I added these holes and strips of bamboo just to give it some dynamism. But the basic shape is has 24 pentagons that fit together. This is a knot. It has 3 crossings, so it's a trefoil. Any 3 crossing knot is a trefoil, and there are different projections of trefoils. This is a continuous strip, and it crosses itself 3 times. And here's another recent piece based on hyperbolic geometry. If you embed a piece of the hyperbolic plane in Euclidean 3 space, you get these kind of wavy surfaces that have negative curvature everywhere, which means that at any point the curvature goes in 2 directions. So this would be positive curvature like the surface of a sphere, and this would be negative curvature like a saddle on a horse. So this is a negative curvature piece with some kind of detailing inspired by coral or cactuses or other plants. So those are some of the kinds of things I do. There's some larger pieces up high, if you can, you can kind of see on the shelf above the piano. There's some larger pieces, but some of them are based on fractal concepts.
The next question: have you ever digged into Gira tilings?
Not in any detail. That refers to these Islamic designs. There's been a lot of work on those. those go back many centuries. So of course they were drawn by hand, and there's methods using, compass and ruler constructions, which can get quite detailed for creating those Islamic designs. And there are different characteristic tiles that appear in those. There's a recent book that goes in depth in Islamic design by J. Bonner, I believe, right? Probably called Islamic, I don't know, you can find it on Amazon or whatever if you search. Reza Sarhanki did some research, has some Bridges papers on Islamic or Persian tilings. So that's really a rich topic and not one I'm an expert on. Craig Kaplan knows a lot about that. I think I may have seen his name in the chat. He's giving a talk tomorrow, actually, not on that topic. But
are there any quasi-periodic hyperbolic tilings?
Quasi-periodic hyperbolic tilings. There should be. I don't recall. Do you recall Bob saying, or anyone else out there?
I don't recall.
Ed says yes, or is that yes to something else? Phil Webster also does some Islamic kind of art. I don't see why there wouldn't be. I've not done much with hyperbolic tiling myself. There are people, again, on Twitter I follow that post hyperbolic stuff all the time.
I would certainly expect so.
Yeah, if you want to explore these topics like spherical tiling or hyperbolic tiling, the Wikipedia articles are pretty good too. And they show all the different regular tessellations and this and that. So that's a pretty good reference.
No substitution tilings in hyperbolic space. Okay. Yeah, no scaling transformation. So that makes sense. That's a good point. So you're not going to have, right, the same sort of substitution construction you do with the Penrose tiles. So it looks like our last question is, I believe I can answer this one, is Robert's shirt tessellated? Yes. Okay. This has been a wonderful talk and a wonderful set of questions. Thank you very much, Robert, and thank you all for attending. And if there's no further questions, we will see you next time.
Yeah, thanks everyone.